Hello, everyone. It's Professor Steve Rehse again. I am so pleased to be with you all on our very special Trick or Treat edition of the DoD K-12 STEM Saturday. Going to be talking about some really interesting things today. First, as always, we have to start off with our land acknowledgement and just reminding everyone that I'm a professor at the University of Windsor, and the University of Windsor sits on the traditional territory of the Three Fires Confederacy of the First Nations, which includes the Ojibwa, the Ottawa, and the Potawatomi. We respect the long-standing relationships with First Nations people in this place in the 100-mile Windsor-Essex Peninsula and the Straits L'Etoile of Detroit. I like to always start off my talks to all of you because not everyone's sure where Windsor is with this beautiful map, thanks to Google Maps, of course, showing this kind of aerial view of where we are located at the University of Windsor. And I think this beautiful picture really gives you an idea of what the Straits L'Etoile of Detroit are, and this beautiful Lake St. Clair. And here's the University of Windsor tucked right in on the banks of the Detroit River, so close to our neighbors and friends in the city of Detroit. So I'm located right here as I'm talking to you now. So let's go ahead and get started with this version of the talk today. And we're going to hear a lot of talks today from the other speakers about the environment and weather and things like that. And what I wanted to talk to you guys about today is what's it like outside right now? And are you hot or cold? Do you need a jacket to go out because you're cold, or do you want to wear a short sleeve shirt because you're hot? Are you hot or cold? But more importantly, to a physicist, what does that mean to be hot or cold? So these are some thoughts on the environment from a physicist. I'm certainly not an environmental scientist, but a physicist thinks about things sometimes just a little bit differently. So there's a lot of talk right now going on about, is the planet getting warmer or is the planet getting colder? So here's our planet getting hot. It's got a temperature, and here it is getting cold. It needs a scarf and a hat. Before you can even begin to ask such questions, you have to think like a scientist. So you need to understand, what does it even mean if you are hot or if you are cold? First things first, you can't even use phrases like hot or cold unless everyone absolutely agrees on what those terms mean. And hot or cold is something everybody knows, kind of. You know when you're hot, you know when you're cold, but what is that? What makes hot? We have to think about that. And these are things that physicists delve right to the beginning of the question. So let me just rephrase here. If you go outside on a very hot day, you feel the hot air. But why? So here's a picture of a young boy. He's obviously outside on a hot day. He is sweating. He is hot. He's been running around in the hot weather, working up a sweat. Sweat's dripping down because he feels the hot air blasting him. But what does that air mean to be hot? If you put a turkey, beautiful Thanksgiving turkey maybe here, in a hot oven, it quickly gets hot and it cooks. That's why you put them in the oven. But why? What is this property of the air that we call hot? Is it a different color? Does it smell different? You see what I mean? What is hot? It's a fundamental question. You put that turkey in a hot oven. The inside of that hot oven could be up to, let's just say, 450 degrees Fahrenheit. There's a way to quantify what we mean by hot. So at least there's a number that goes with it. So here's a picture of a thermometer, and it's saying it's 450 degrees Fahrenheit. That would be something that you would set the oven to when you cook a turkey. In Canada, we actually don't use that Fahrenheit scale. We use something called Celsius or centigrade. So in Canada, 450 degrees Fahrenheit, we would report the exact same hotness as 232 degrees Celsius or 232 centigrade. So we would call it 232 degrees C right there. The thing is, in physics, we actually use a third unit of temperature. So in America, you might say, oh, that oven's 450 degrees Fahrenheit. In Canada, you might say that oven is 232 degrees Celsius or centigrade. A physicist would say, oh, that oven is 505 Kelvin, degrees Kelvin. So to get degrees Kelvin, you take the degrees in Celsius and you add 273. So it's actually a pretty easy conversion. So these are the units of degrees Kelvin. And this is named after William Thomson, the first Baron Kelvin. And something that we do in physics, if you look at it, so you all know that little O symbol that goes up by the number, that's the degree symbol, and you use it when you write the temperature. In physics, when you use degrees Kelvin, you don't ever use that degree symbol with it. So it's still a degree, but we don't have that degree symbol. So it's 505 Kelvin would be a way to report the temperature of that oven. So that was the hot oven. What if you go outside? You can't make your oven cold, but say you go outside. You're up in northern Michigan. For sure it can get this cold. You go outside on a freezing cold day. You better wear your hat. You better wear your gloves. It's minus 40 degrees Fahrenheit. That would be really cold. Turns out minus 40 degrees Fahrenheit is actually the same as minus 40 degrees Celsius. Minus 40 is the one temperature that's the same in the Fahrenheit and the Celsius scales. And of course, you do the trick of adding 273 to that, and you'll see that minus 40 degrees C is 233 Kelvin. So it's a minus negative temperature here, a minus negative temperature here, but the temperature in degrees Kelvin is still positive, and that's going to be one of our keys to why we use the Kelvin scale in physics. Because in fact, degrees Kelvin can never be negative. It must always be a non-negative number. So what that means is that the coldest anything can be ever is 0 Kelvin, or sometimes we write that as 0 K. So just for example, we have water boiling at 373 K, water freezing at 273 K, all positive. And then at the very bottom of the scale, nothing anywhere ever can be colder than 0 K. And we call that absolute zero. So it turns out there's not really a limit to how hot something can be, but there's a limit, there's a bottom to how cold it can be. Nothing can ever be colder than absolute zero, which is 0 Kelvin. Why is that? Why can there's no end to how hot something can get, but there is a bottom to how cold something can get? Well, here's the explanation. And this is what I mean by what does it mean to be hot or cold? You have to really think about what it means. And what it means is temperature means speed. This is easiest to understand in gases, although it's also true in liquids and in solids, but let's just talk about gases. Temperature means speed. If air is hot, what that means is the molecules of air are actually moving faster than the molecules in cold air. So it literally is the speed with which these molecules, and I'm showing them animated on the screen in front of you. You can't see the molecules of air, of course, when you go outside, you don't see anything, but it means they're moving really fast and they're slamming into you. All right, so how fast on a hot day? Well, those molecules of air are maybe going about 1,200 meters per second, which is pretty fast. It's several times faster than a bullet can travel. So that's actually pretty fast. Why does that make you hot? Well, if those molecules are moving really fast, they're covering a lot of ground, and so they're running into you a lot, and they're slamming into you all over your body. And every time they hit you, they're transferring some of that energy. When they're moving really fast, that velocity, that speed, gives them a lot of what we call kinetic energy. And when it runs into you, it gives you some of that energy. And then they bounce off and go off on their way, but they're not moving as fast after they hit you. They've given some of their energy to you, and that makes you get hot as well. So they're giving their energy to you after they collide all over your body, millions and millions of times a second. So that makes you hot too. So you've taken their energy. Why'd you take their energy? You don't have any choice in it. It just happens. Well, again, let's just remind ourselves, temperature means speed. So if the air is cold, the molecules of air are moving more slowly. So you can see in the animation I've created here, those molecules are just kind of moving around, not nearly as fast as the fast hot air. So how slow is slow? It's definitely not as slow as I'm showing on the screen. Definitely. It's still about 1,000 meters per second, which is very, very fast. All right. But it is slower than the molecules of the hot air, for sure. So what happens then? Well, here's a kid, he's laying in the snow, he's starting to get cold. If those molecules are moving slowly, when they run into you, then you transfer some of your energy, your warmth, your heat energy to them. When they rebound off you, they can be moving faster. But of course, that leaves you feeling cold, right? So the feeling that you have of coldness is you're giving your thermal energy to all the cold things, the slow moving things that are running into you. They can collide with you. They're going to pick up energy and rebound, moving a little more quickly. They're stealing your energy away from you. Why'd you give them your energy? Again, you didn't really have any say in the matter. You can't stop any of those collisions of those air molecules with you, but you are giving up your thermal heat energy to get those molecules moving more fastly. And that's what we mean by cold. All right. So it all has to do with the velocity of the atoms that are carrying this energy around. So if temperature equals speed, which it certainly does, think about something moving. Something can always go a little faster, right? Whatever speed you're going, I mean, you've all been in a car going down the highway. You can always go a little faster, can't you? If you're going 55 miles an hour, you could go 60. If you're going 65 miles an hour, you can go 70. But nothing can go slower than not moving. If you hit the brakes and come to a complete stop, what is slower than not moving? Nothing. Do you see what I mean? There is a limit to velocity or speed. You can't go slower than 0. So if temperature equals speed, then no movement equals no speed, and no speed then means no temperature, and no temperature means absolute 0, as we talked about before. That's why there's a floor to how cold things can get. Absolute 0 is the point at which there is no temperature, and no temperature means there's nothing moving. 0 movement at all, which is no speed. All of this is summarized in physics in what we call the kinetic theory of gases. And I don't want to go into that too much, but the kinetic theory of gases allows you to drive a pretty simple equation, which I'm showing down here. It looks like this. Basically, it's a bunch of constants and a bunch of numbers, which are not that important, but it relates the speed, what we call the velocity in physics, or V, that's right here, to the temperature, T, of those molecules as well. So there's an equal sign in the middle, and that just means that as V goes up on this side of the equation, the temperature, or T, must go up on this side of the equation. As V goes down on this side of the equation, the temperature T has to go down on this side of the equation. And because there's an equal sign in the middle, if V equals 0, then T must be 0. And this is why we use the Kelvin scale. And that place where V equals 0 means T equals 0, that is absolute 0. So the last thing to know in this talk is that this is something really cool. Nothing can ever actually get to absolute 0. It's not physically possible, although it is the limit of the coldest thing that could ever be. To actually reach and be at absolute 0 is forbidden by the super cool laws of physics. We can get close, but we can't ever get to 0 itself. It's not that we have to try harder and get there. It is forbidden by the laws of physics. Nothing can ever be at an absolute 0 temperature. So how cold can we get? Well, physicists are pretty clever and we're doing pretty well. So again, let's remind ourselves of the scale here, that water boils at 373 Kelvin. I looked it up and it turns out the coldest day on Earth on record is 184 Kelvin. So that's really cold, but again, still 184 Kelvin, it's not anywhere near 0. So you would think, well, maybe the coldest place in the universe is the middle of empty, cold, dark space. No, turns out the middle of empty, cold, dark space, 3 Kelvin. So very, very, very cold, but nowhere near 0. So the coldest place in the universe is actually a physics lab at MIT, the Massachusetts Institute of Technology, where they have a little cloud of atoms, which you can see glowing right here at 80 nanokelvin. So NK is the unit for nanokelvin, and nano means it's 80 billionths of a degree Kelvin. So if you wrote it, you'd have to put all these 0 in, 0.000000080 Kelvin, 80 billionths of a degree Kelvin. And it's in this glowing cloud of atoms here. And this is a physicist, Professor Wolfgang Ketterle at the Massachusetts Institute of Technology, looking at this very cold cloud of atoms, which we call a Bose-Einstein condensate, the coldest place in the universe, as far as we know, created by a physicist in a lab. Why can things never get to absolute 0? Well, it turns out when things get really cold, like that condensate, that little cloud of billionths of a degree Kelvin in Professor Ketterle's lab, things get really, really, really weird. Of course, for a physicist, we love that. Things get super interesting. And unlike anything you experience in your everyday life, it's very, very complicated, but super cool things start to happen when things get really cold like that. Unfortunately, that's a talk for another day. We definitely don't have time to get into it now, but it's a really interesting thing to think about, what the possibilities are of things that you kind of know in your everyday life, hot and cold, and what that means when you take it to one extreme or another. So hopefully someday we'll get to talk about all of that, but we just don't have time today. So remember, hot or cold means fast or slow. That's true for solids as well as liquids and gases. But if you're ever just wondering what is hot and cold being, basically just remember it means the molecules or the things that make it up are either moving fast, quickly, or they're moving slowly. And then that relates to the property of hotness or coldness that we then measure with a temperature scale in our life. And that's essentially how it's all working. That's all I have for today. Thanks everyone for paying attention. I will hang around for a little while here, put some questions down in the chat. We can hang around and talk about those. I very much appreciated the time I had to talk to you all, and we're going to do this again real soon. But for now, maybe we can take some questions in the chat. So thanks a lot, everybody. I much appreciate it.